Thank you very much for inviting me to speak here. I'm very happy and honored to be in Poland for the first time. Today I'll be talking about Thunderclap, which is a set of novel security vulnerabilities related to the way that peripheral devices, such as graphics cards and network cards, communicate with computer systems. I'll also be discussing a novel research platform that my team and I built to investigate these vulnerabilities and develop proof-of-concept exploits using them. So before we get started, I'll just share a little bit about myself and about this work. I'm currently a PhD student at the University of Cambridge. I work in the security group in the Department of Computer Science. And I've been working on IO security in this field, or the security of peripheral devices, since 2016. This work I'm going to discuss today on Thunderclap was first presented publicly in February of this year, just a few months ago, at the Network and Distributed System Security Symposium. So it's quite recent. And I'd like to draw attention to the fact that this is indeed joint work. So I'd like to gratefully acknowledge the support of my research group and also my close collaborators on this project, Theo Marketos and Colin Rothwell. So the main point of this talk will be a deep technical dive that builds up to an example proof of concept attack that uses our research platform to own a machine running macOS. But before kind of digging into the technical bits, I want to start with some high-level introductory points about peripheral device security in general. So the first point is that hot pluggable interconnects like Thunderbolt completely change the threat model of peripheral devices. In a traditional worldview, peripheral devices were produced by a trusted manufacturer, and the only way to connect them to a computer system would be to plug them directly into a motherboard on the inside of a machine's case. And so this graphics card in the bottom left is an example of such a traditional peripheral device that can only be connected by being plugged in via PCI on the inside of a machine's case. However, with the rise of hot pluggable interconnects like Thunderbolt, it's now possible to connect peripheral devices to a machine via a port on the outside of its case. And in the case of hot pluggable interconnects, even while the system is running. So while it may not have been reasonable in old days for an attacker to come up to a machine, install a malicious peripheral device on the inside of its case, and carry out an exploit without being detected, it's much more likely, for example, that an attacker would walk up to an unattended laptop with a Thunderbolt port, plug in some malicious peripheral device, carry out an exploit, and walk away in a matter of seconds without being detected. And this suggests that going forward, in a Thunderbolt-enabled world, we should no longer be considering peripheral devices as trustworthy. So the other two graphics here, one is an example of a Thunderbolt connection, and the other is an example of the many dongles that you need if your machines support Thunderbolt to plug anything useful in. The second high-level point I'd like to make is that modern machines running macOS, Windows, Linux, and FreeBSD are vulnerable to malicious peripheral devices, even with the most recent security patches and updates applied. We'll effectively spend the rest of this talk demonstrating this fact by going through some proof-of-concept exploits that work against current machines. And the third and final high-level point is that Thunderbolt 3, which is the newest and most widely deployed version of Thunderbolt, combines power input for charging, video output for projecting or for using an external display, and peripheral device access over the same physical port. And this greatly increases the threat of peripheral device attacks in practice, because we could imagine a public charging station in an airport or even a projector like this at a conference that connect to your machine via Thunderbolt. And they even perform their advertised functions of charging your device and projecting video, but simultaneously abuse the peripheral device access to own your machine without your knowing. Okay, so with those kind of high-level points out of the way, let's now dive into the technical bit. And first, we'll start talking about some background, how peripheral devices and computer systems, operating systems communicate. So in existing architectures, peripheral devices have what's called direct memory access, or DMA, which effectively allows them to access physical memory of a system without any kind of processor intervention. So this is kind of a schematic architectural diagram here. And we can see at the top we have a CPU, which is running some processes. And processes work with virtual addresses. Now, the only way for those virtual addresses to be converted into physical addresses and then ultimately used to access memory is if they first pass through the memory management unit, or MMU. And the MMU is a piece of hardware controlled by the operating system that basically allows the OS to make mappings at a fine-grained level between a virtual address and a physical address. So the only way for a process to access any bit of main memory in this scenario is if its virtual address first passes through the IOMMU and the operating system has explicitly granted access to the bit of physical memory that it's going to access. Now, in contrast to that, at the bottom of this diagram, we can see a peripheral device, which operates directly with physical addresses, which means it can essentially, without any kind of intervention by the operating system, access read and write kind of arbitrary locations in memory. We'll come back to that in a second. But two more points that are important about direct memory access. It's facilitated by the system bus, which is canonically PCI Express, or PCIe in modern systems. And PCIe is quite a complicated interconnect, but for our purposes here, we can just think of it as a packet-switched interconnect that connects together all of the peripheral devices on a system with the CPU cores and memory as well. So over this interconnect, a peripheral device can ask to read or write some region of memory, and that request will be granted. Now, another important thing about PCIe is, as I mentioned at the beginning, it can be exposed over hot pluggable interconnects. So this diagram here shows that Thunderbolt, among other things, multiplexes PCI Express and DisplayPort, which is a protocol for kind of external displays, and makes them available on the outside of a machine's case through the Thunderbolt port. So this effectively means that when you plug in a Thunderbolt device to your machine, you are giving it access directly to physical memory in this worldview. Now, anything with arbitrary access to physical memory can basically bypass any arbitrary operating system security policy. This is because the main way that modern operating systems enforce their security policies is by restricting and isolating regions of memory from access. So I'll say that again to let it sink in. You know, if a peripheral device has arbitrary access to physical memory, it can effectively do whatever it wants. It totally owns the machine. So when a peripheral device abuses this memory access to violate some security policy, it's said to have carried out a DMA attack. And DMA attacks have been kind of widely understood and published about for at least the last 15 years. And they all work in the same kind of broad way. They scan through all of physical memory and look for sensitive signatures in memory that would indicate either sensitive information that they can exfiltrate or a sensitive data or control structure they can modify to change the operating system or the computer system itself's behavior. So, for example, DMA attacks have been published and shown, also used in the wild, and shown to be able to unlock machines, escalate privilege, bypass disk encryption, dump memory, execute arbitrary Metasploit payloads, you name it. As I said, if you have arbitrary access to physical memory, you totally own the machine. Luckily, for more modern architectures, the picture is not so grim. Peripheral devices can't just own your machine willy-nilly. Modern architectures have I/O memory management units, or IOMMUs, which are basically analogous to the memory management units, or MMUs. And they allow the operating system to govern peripheral device memory access, just as the MMUs allow it to govern process memory access. So effectively, in an IOMMU-enabled world, peripheral devices work with virtual addresses as well. We call them I/O virtual addresses. And the only way for a peripheral device, or the only way for these I/O virtual addresses to be ultimately translated into physical addresses and used to access memory is if the operating system has explicitly granted that right. So how are IOMMUs actually used in modern operating systems? That's a tongue twister. So peripheral device drivers use these functions that are exposed by the IOMMU driver itself to facilitate DMA communication. So for example, if we are the driver for a network card, a NIC, we might want to expose some packet data to our NIC so that it can be transmitted. And we're going to do that via the IOMMU. So first, we would call the map function. And we would specify the network card that we want the memory to be exposed to. We would point to the region of memory and give its length as well. And we'd also give some permissions like read or write or both. This function will open a window through the IOMMU to that region of physical memory, and it will return an IO virtual address that our network card driver can then give to the network card itself. And then the network card can use that address to access the memory. Then, once the communication is finished, the network card driver would call the unmap function. And what the unmap function will do is basically revoke the peripheral device's access to that region of memory. So one important note here is that the operating system can use the IOMMU to isolate peripheral devices in separate virtual address spaces. This means that it can expose a region of memory to one peripheral device, but not another. And this will come back later when we're going through our exploit. So just keep that in mind. So in a world with the IOMMU enabled, are DMA attacks still possible? Well, existing DMA attacks don't work at all, and they don't work for two main reasons. The first reason is that previous DMA attack devices are not recognized by the operating system. In particular, the operating system doesn't have any kind of driver that recognizes this malicious device that's going to be plugged in, so no driver will attach, and then no driver will be opening actually windows of memory via the IOMMU for the malicious attack device to access. So for all of these previous DMA attack devices, if the IOMMU is enabled, they won't have any access to memory at all, and therefore they can't carry out their attacks. But secondly, even if windows of memory were open for these DMA attack devices, their strategy wouldn't work either, because past DMA attacks have relied on scanning all of physical memory looking for sensitive signatures. But in the IOMMU-enabled world, these attack devices would only have access to the precise windows that have been opened up to them, not all of physical memory. So the attacks will no longer work. So previous DMA attacks not working with the IOMMU-enabled has led to a kind of widespread belief that IOMMU use prevents DMA attacks in general. And this is not true, otherwise I wouldn't be here talking to you today. And so we'll see for the rest of this talk novel attacks that work even against a system with the IOMMU enabled. Okay, so now that that background's out of the way, I'll briefly introduce the Thunderclap platform, which is kind of the research platform and malicious peripheral attack device that we use to carry out our exploits. So we just saw that in the IOMMU enabled world, no previous DMA attack devices work. So what we would like to do now is formulate a model for an attacker that might work even against a system with the IOMMU enabled. And our model is as follows. We consider a malicious peripheral device that can emulate the functionality of a legitimate peripheral device so that it will appear to the operating system as a device that the OS recognizes, and therefore a driver will attach and then start opening windows in the IOMMU for our malicious peripheral attack device to access. Simultaneously with this emulation, our attack device will also make arbitrary malicious DMA requests, basically investigating what data are available to it in the windows opened via the IOMMU in an attempt to compromise the system. And it's important we don't assume to have any control over code running on the target system or any control over the target system of any other kind. So to instantiate this attacker model in reality, my team and I developed the Thunderclap platform, which is really quite a complicated piece of engineering. Many complex engineering problems were solved and research questions were answered as we built this. And there's much more detail about the Thunderclap platform itself in our paper and on our website. I'll talk more about that in a bit. But for now, I'll just cover kind of the main important things for using it in our exploit. The main idea behind the Thunderclap platform is that we use QEMU, which is a software system emulator, that in particular supports emulation for a number of different peripheral device models. So this is basically software models of the behavior of various peripheral devices that will basically emulate their behavior exactly. And we're going to connect QEMU's peripheral device models in software to a real hardware PCIe core. So that when QEMU would normally be emulating some DMA transaction with an emulated system host or an emulated attack machine, target machine, instead, we're going to have the emulated DMA transactions go through a real PCIe core and talk to a real target victim machine. So then the victim machine will think that it's talking to a real PCIe device and will be quite happy. And the QEMU device model will also be quite happy talking to a real machine rather than a QEMU emulated one. And then simultaneously with this emulation, as I mentioned, we'll run a malicious payload concurrently that will allow us to investigate what data is actually exposed in the windows in the IOMMU that are open to us and see if we can make anything malicious happen. So to build Thunderclap in reality, we use an FPGA. And basically on this FPGA, we have an ARM core, which you can see down there on the right. On top of the ARM core, we're running the Linux kernel and also a modified version of QEMU, as I mentioned. And this version of QEMU is going to be emulating peripheral devices. And we also synthesized a PCIe core on this FPGA, and the version of QEMU is plumbed together with that PCIe core so that when it's actually emulating a DMA transaction, that transaction will go over the PCIe core and then through the PCIe connector of the FPGA itself. So this FPGA could then be plugged in to the motherboard of some victim machine on the inside of its case, as we discussed at the beginning, or we could connect Thunderclap to a PCIe to Thunderbolt bridge, which would allow it to be plugged into a Thunderbolt port on the outside of a machine's case, and then carry out the kind of more threatening DMA attacks that we mentioned at the beginning. In this example configuration, this detail is not incredibly important, but Thunderclap is configured to emulate a network card, a NIC. And it is possible in theory to configure Thunderclap to emulate any device that QEMU has a device model for. Okay, so now that we've established the basics of the Thunderclap platform, we can talk about a proof of concept attack. And with an attack, it first has to have a vulnerability that we're going to work with here. And in particular, we'll be focusing on the vulnerability we identified, which we call the spatial vulnerability. And it basically stems from the fact that the IOMMU views memory as a sequence of 4 kilobyte chunks or pages. And if you're familiar with memory management units, this should be kind of familiar to you. But in particular, mappings in the IOMMU are made at page granularity, which means that when you're mapping from some IO virtual address to a physical address, you can only map regions of memory whose sizes are a multiple of 4 kilobytes. And so this could be a potential problem if we have a buffer for device communication that we need to map to some peripheral device that's less than 4 kilobytes in size. Because as we can see from this diagram here, which represents basically, this big square or big box is one page in memory, so a 4 kilobyte chunk of memory. And it's laid out kind of like a 2D byte array where the first entry is at the top left and the last entry is at the bottom right. We can see in this diagram that we have a small buffer for device communication there in blue. And really, that's the only buffer that the device needs to be able to communicate with. But when we expose that to the device, the sensitive data around that buffer will also be exposed to the device because it's co-located on the same page. And this sensitive data could be, metadata associated with the data structure or other kind of sensitive information that we don't want a device to be able to access. And also we can see there could be co-located on that same page a different data structure completely unrelated. The kernel memory allocator just decided to put it there. That is also going to be exposed to the device. So this is just one of the vulnerabilities that we identified in current IOMMU usage, and there are some additional ones in the paper, which I'll refer you to if you're curious about more. But so the plan for our proof of concept exploit here will be to have Thunderclap emulate an Intel E1000 network card. And the reason we chose an E1000 network card is because of its kind of widespread support across, its widespread driver support across various operating systems. And our plan of attack will be to exploit the spatial vulnerability using network card related data structures in macOS to gain arbitrary privileged code execution. So basically, we will be able to run whatever code we want as the kernel, which means we totally own the macOS machine. So before getting into the particulars of the attack, we first need to understand some data structures related to how a network card and the operating system communicate. And the first one of interest is the network card descriptor ring, the NIC-specific descriptor ring. This is essentially a memory resident buffer, and each entry in the buffer is called a descriptor. It contains an IO virtual address that the NIC can follow that points to some buffer that's used to store packet data. It also contains the length of that buffer. And effectively, these pointers to packet data will be used to kind of instruct the NIC where it needs to be transmitting and receiving information from. So just for a kind of example use, if the operating system wants to transmit a packet over the network card, it will first map the packet data into the network card's virtual address space through the IOMMU. It will then get an IO virtual address that it will add to the descriptor ring. And then it will tell the network card that there's some packet data outstanding to be transmitted, and the network card will make that transmission. So that's roughly how this data structure works. What will be more important for our attack, though, is the operating system-specific packet data structure, which are actually used to manage basically packet data buffers. And these contain the packet data itself in addition to some metadata. And this data structure itself will provide the attack vector that we're going to use in our proof of concept exploit. So we're going to drill down into what this data structure looks like in macOS. In macOS, the data structure used for managing packet data is called the mbuf. This derives from FreeBSD, so if you're familiar with FreeBSD at all, this might be familiar to you. And mbufs are quite complicated data structures due to, for kind of performance concerns. They've been designed in such a way that allows certain things to be quite fast, but complicates them. So we're going to go over the parts of the mbuf that are relevant for our attack only. And the first interesting thing about them is that mbufs can have either internal packet data or external packet data. So in this diagram here, we see two mbufs that are connected together in kind of a linked list structure. And the one on the left has internal packet data, the one on the right has external. Now, the internal packet data is actually quite small, and it's going to be part of the mbuf data structure itself. So it's going to be contiguous or right next to the mbuf metadata. This small internal packet data might be used to store something like a packet header. And on the right, we see an mbuf with external packet data. This external packet data can potentially be quite large, up to many kilobytes in size. It will be allocated separately from the mbuf data structure itself. So in particular, it will be stored on a different page in memory from the mbuf metadata. The second interesting thing here is that the mbuf with external packet data actually has a custom free function pointer. And the point of this free function pointer is that when the mbuf itself is freed, this free function pointer will be called such that, and the idea of it is that it'll handle freeing the memory for the external packet data itself, so that there aren't any memory leaks when the mbuf with external packet data is freed. But this is kind of interesting because here we have a function pointer that the kernel is going to jump to. And it would be pretty interesting from an attacker's point of view if we could inject a code pointer here and then convince the kernel to jump basically wherever we want. However, there's one problem, which is, as I mentioned, the point of these buffers is to kind of manage data that the NIC is going to transmit or receive. And so the NIC only needs access to the actual packet data itself. And in the case of the mbuf with external packet data, we mentioned that the external packet data is stored on a separate page from the mbuf metadata. So actually, the network card won't be able, or Thunderclap, masquerading as a network card, won't actually be able to access the mbuf metadata for an mbuf that has external packet data. And this kind of red overlay that I've included in the graphic shows basically what Thunderclap is able to access in memory. But an interesting thing here is that we can access the mbuf metadata when we're given an mbuf with internal packet data. As I mentioned, because they're located on the same page. And this kind of gives us the idea for an attack. When Thunderclap is given an mbuf with internal packet data, for example, anytime the victim machine wants to transmit a packet, and the header might be in an mbuf that looks like this, we will modify the metadata of that mbuf, switch some flags around, etc. It's actually a little more complicated than that, but for our purposes here, it doesn't matter. We'll make the mbuf look like it has external packet data, and we're then going to inject the code pointer for the custom free function. And the idea here is that when the mbuf is ultimately freed, the kernel will jump to the code pointer that we injected and run whatever code we want. So what does this attack look like in practice? So here we'll have a diagram with our victim macOS machine on the left in green and the malicious Thunderclap NIC on the right in red. And they're connected via PCIe, but they may be talking over a Thunderbolt interface as well. So the first thing that would happen is we plug the malicious NIC in via Thunderbolt port. And during the device discovery and driver attachment phase, the victim machine will ask Thunderclap what it is. Thunderclap will respond by saying it's an Intel E1000, and it will do that by emulating the appropriate PCI device ID and any other kind of configuration things that it needs to emulate using QEMU. Then the victim machine won't suspect that anything is wrong. It will set up all the memory resident data structures that it needs to communicate with the network card, like the descriptor ring we mentioned and others. And then critically here, the malicious network card will function normally. It will use QEMU to emulate the behavior of a network card, and it will also use QEMU's virtual network stack to understand basic protocols like DHCP and others, such that there will be no reason for the victim machine to think that anything is going wrong here. Then, whenever the victim machine wants to transmit some packet, it will tell Thunderclap that it's added an mbuf with internal storage to the descriptor ring for it to send. At this point, the malicious payload will trigger, we'll overwrite the mbuf metadata, inject our custom free function pointer, and then we'll tell the operating system that the packet has been transmitted. At that point, the operating system will free the mbuf, the custom free function will be called, and the operating system will be running whatever code we point to with kernel privilege. So this means that we completely own the machine. Just some remarks about this attack vector. It's really trivially easy to get a root shell using this attack vector. Because there's a function in the macOS kernel called kuncexecute, which will basically execute a given binary as some given user ID. So if you pass in the equivalent of terminal.app and a user ID of 0, then a root shell pops up, and that's very interesting. One thing that I didn't mention before is that not only can we inject a custom free function pointer here, but we can also control the arguments that would be passed to that function. So that makes this root shell very easy to get. And then a second remark is that because we can inject an arbitrary code pointer here, jump-oriented programming and return-oriented programming style attacks are possible, which basically allow us to execute arbitrary code as the kernel. This really means that we can basically take our Thunderclap attack device, plug it into an unintended macOS laptop, and just completely own it in a matter of seconds. So that is very interesting. Now, in practice, there's only one roadblock that makes this attack slightly less elegant than I've just described it, and that is KASLR, or Kernel Address Space Layout Randomization. And this is a security mitigation employed by macOS, and effectively what it does is it adds a random integer slide, or a random slide, which is an integer multiple of 2 megabytes, to every kernel symbol address at boot time. So the idea here is that the kernel code will be shifted by some random amount, and the attacker won't be able to guess what that random amount is ahead of time. So even if the attacker can overwrite some code pointer, they won't be able to gauge precisely where into the kernel code they'll jump, so they won't be able to do anything sophisticated. They may be able to crash the machine or do some other weird stuff, but nothing sophisticated. So to make that a little more concrete, we have an example here. We have a kernel symbol address that we can just get by running nm on the binary of the kernel. And let's say it looks like this. It's a many Fs and then 80,000 and a cafe in hex. And then the kernel slide at boot time is chosen randomly. We can say it's randomly chosen. The number 123 is chosen. And so 123 times 2 megabytes is then added to every kernel symbol address. So the slid symbol address looks like at what we get in the third row. And just one important thing to note here, which will be relevant on the next slide, is that the last 5 hex digits here, a cafe, remain the same. And that's because the kernel slide is a multiple of 2 megabytes. So the question now is, how do we bypass KASLR as Thunderclap? Well, macOS kind of makes 2 very interesting choices in the way that it uses the IOMMU that allow us to do so rather easily. The first thing it does is that it uses a single address space for all peripheral devices. So remember I mentioned a while ago now that operating systems can use the IOMMU to isolate peripheral devices in their own virtual address space. macOS chooses to use a single address space for all peripheral devices. This means, among other there are tons of security problems associated with this, which we don't have time to go into. But the main idea here is that when we plug Thunderclap in, and windows are being opened for it as a malicious network card, it will also be able to access every other bit of memory that's exposed to every other peripheral device on the system. And this kind of goes quite well with the second interesting choice they made, which is that their USB and AHCI drivers leak the slid address of a particular kernel symbol in the memory that they expose to peripheral devices. So this gives us the idea of how we can bypass KASLR from Thunderclap. In our malicious payload, we scan all of the memory that's exposed to us, meaning all the memory available to all peripheral devices, and we look for the unchanged lower 5 hex digits of a kernel symbol that we know ahead of time is going to be leaked. When we find those lower 5 hex digits in memory, we know that what we're actually looking at is the slid kernel address of a particular symbol that we know. So then we can take the static address of that symbol, which we can get from the binary, subtract it from the slid address, and then we have the KASLR slide. And with the KASLR slide, you can basically do any kind of precise attacks that you want, and the mitigation doesn't work. So just to make that a bit more concrete, we can look from Thunderclap, we can look through all of memory, looking for the signature, the byte signature that here is in red, a cafe. And what we will find is the last part of the third row, which is the slid kernel symbol address for some particular symbol. We know the kernel symbol's static address because we can get it from the binary itself, and that's the first row. And when we subtract the first row from the third row, we get the second row, which is the KASLR slide, and that's basically the secret that the mitigation depends on. So we can break that mitigation quite easily. Okay, so now just some remarks on this example attack that we saw. So here we targeted only one vulnerability, which was the spatial vulnerability. We targeted one emulated device, which is a network card, one operating system, macOS, and one specific attack vector, which is one particular code pointer that we injected. Each one of these points that we fixed could be varied significantly. There are other vulnerabilities we identified. We can emulate any device available to TOMMU theoretically. We can target any operating system, and even when you fix all of the other points, there are many, many, many attack vectors available for any particular operating system. We have more examples in our paper of different styles of attacks, targeting different operating systems, etc. But in general, when we're thinking about what data are actually exposed to peripheral devices in these IOMMU windows, the attack surface is quite complex. Because these peripheral devices, our malicious peripheral devices, can potentially interact with data structures that involve many, many system components, including kernel memory allocators, I/O subsystems, and all kinds of device drivers. This makes them kind of hard to reason about, and in particular, hard to defend. And a final point here is that all of the operating systems we examined as part of this work had issues with their IOMMU usage that go beyond the Thunderclap vulnerabilities, which were universal. So we saw in macOS that every peripheral device is put in a single address space, and they also leak a slid kernel symbol address, which end up being two significant problems. But in FreeBSD, Linux, and Windows, among other issues that they have when you enable their IOMMU protections, the IOMMU was actually disabled by default when we started this work. So all that time I spent telling you about how old DMA attacks don't work anymore and attackers everywhere are very sad is actually not true. Because when we started this work, the IOMMU was not enabled by default and all of those old style DMA attacks still worked. So that was concerning. Okay, so that kind of wraps up our proof of concept attack. And now I just want to spend a little bit of time talking about mitigation efforts. Because after all, the whole point of this security research is that hopefully we identify problems before they can be actually exploited in the wild for malicious purposes, and we get them fixed. So with that in mind, let's take a look at vendor response to this issue. So we've been working with vendors since 2016, when we first kind of started doing this work and started identifying some serious problems. And vendors that we've corresponded with have responded in kind of varying ways. macOS mitigated the specific attack that we just went through in version 10.12.4. And they mitigated the attack in a very particular way. Specifically, they encrypted the particular function pointer that we inject with some cookie that's not available to any peripheral device. So this does technically stop the attack that I just showed you, which is a good thing. But it doesn't really do anything to address the underlying Thunderclap vulnerabilities. Windows and Linux, after kind of corresponding with us, have decided to enable their baseline IOMMU support by default for peripheral devices that are connected over Thunderbolt. And this is a very good thing. It's progress. It means that the old style DMA attacks no longer work when they're inserted, when the malicious peripheral DMA devices are inserted via a port on the outside of a machine's case. However, with baseline IOMMU support, the Thunderclap vulnerabilities that we identified still apply. And FreeBSD indicated that these Thunderclap attacks are out of scope for their security model. But FreeBSD also doesn't support Thunderbolt hot plugging. So it seems like their approach here is to reduce the threat of these attacks by not allowing peripheral devices to be hot plugged into the outside of a machine's case. Another interesting point is a major laptop vendor indicated that they won't ship Thunderbolt in any of their devices until they better understand these attacks and their implications. So people are taking this kind of seriously. But to sum up, this is progress, but the Thunderclap vulnerabilities in general still apply. So we're making progress, but there's still a lot of work and open questions to be addressed. Speaking of those open questions, maybe let's take a look now at how we might address the spatial vulnerability we identified in general. What kind of mitigations might we be able to apply to the kernel or to hardware to actually fix the underlying problem here? It seems like there are two main approaches. One could be to change the way that kernel memory allocators work and kernel data structures, such that buffers for device communication are isolated on their own pages in memory. This means that every time you expose a buffer for device communication, it would be guaranteed that nothing else sensitive would be located on that page and the spatial vulnerability would go away. This seems somewhat feasible, but it definitely involves significant engineering efforts on the part of kernel engineers, and changing these data structures could have performance implications, and it could also result in a pretty inefficient use of memory if you have to allocate a 4 kilobyte page for potentially very small buffers and millions of times a second. The second potential way of fixing this issue might be to change the IOMMU hardware itself to support arbitrary mapping granularity rather than page granularity. And this also seems kind of feasible, but it would require significant hardware engineering effort. And the IOMMU hardware is also used for other things beyond protecting from malicious peripheral devices, in particular in virtualization. And so changing the hardware in this way may have consequences there that need to be investigated. So to summarize, it seems like it would be feasible to fix this vulnerability, to fix the underlying problem, but there's significant engineering effort required, and there's kind of performance security trade-offs that need to be better understood. So this is kind of an open area of current research and an open challenge. Okay, so now let's have some concluding remarks and talk about, kind of summarize what we've talked about here. So I introduced novel attacks from malicious peripheral devices that are effective even against IOMMU-enabled systems. That was the Thunderclap vulnerabilities and using the Thunderclap platform to carry out some novel attacks. We made the point at the beginning that hot pluggable interconnects like Thunderbolt 3 that offer power, video, and DMA over the same port greatly increase the threat of these attacks. And the examples that we considered were, at an airport, a public charging station that plugs into your Thunderbolt port and charges your machine, but also owns your machine. Or, for example, a similar thing going on at a conference with a Thunderbolt projector. We saw that vendors are engaged on this issue and starting to harden their products, but addressing the underlying issues in general kind of still remains an open challenge. And so kind of my parting word of advice will be something that's often repeated, but still great advice, which is continue to stay vigilant about what you plug into your machines, especially if you're plugging them in over a Thunderbolt port, because you could be giving them access to memory. Okay, and finally here, I want to mention, in kind of developing the Thunderclap platform, we addressed a number of complicated engineering challenges, research questions, and basically it was really hard and took a lot of time. And we think that this field now is open for other people. It's kind of, there's ripe things for investigation, and we think there's potential for other people who are either working in this field or interested in getting involved to kind of get up to speed and join us here. And so to that end, we've kind of made everything that we've done open source, and we've packaged all our software and made it so that people who want to get involved will have a much easier time than us. They won't have to build their own research platform, etc. So on our website here, thunderclap.io, we have free access to our paper. We have a getting started guide, including any hardware that you may need to buy to create Thunderclap in your own, and all our packaged software that you may need to download and install. Yeah, as I just mentioned, all our software is open source on GitHub and packaged, so it should be relatively easy to install. And we also have a mailing list for users, which is linked here. And you're welcome to join. And if you're interested in getting started, you can send us an email on this list, and we'll be happy to help you. Finally, here's the citation for our paper. And I'll reiterate that we only had time today to go through a very, very small percentage of what's actually possible here with this kind of whole new attack vector and attack area and vulnerability space. So if you're interested in more information, please check out our paper. Yeah, that's all I can say. With that, Dziękuję bardzo. Thank you very much for listening. Yeah. So if we have, thank you very much. If we have time, I'm happy to take some questions now. Or if you have a question that's better suited to email, feel free to send me mail. My address is there.
Works? Okay. Quick question. What about adding, as a mitigation factor, what about adding the sort of authentication between the hardware device and the rest of the machine? I mean, real certificates
like public
and so forth.
Yeah.
Exactly.
Yeah, so there
like
is...
with a code, because it's a, in fact, it's a code. So.
Yes, so I think this is a possibility. And in fact, I believe there is a PCI authentication spec which is floating out there. I'm not sure that it's widely used. And I think, yeah, that is a reasonable possibility for preventing these kind of attacks. It would have the problems that are kind of standard with public key infrastructure and this kind of thing. But yeah, it is a good thing. And I should mention, I have this kind of backup slide about it. Thunderbolt as well does have access control that can be sort of used to authenticate devices at the Thunderbolt level. But there are a number of problems with it, including, most interestingly, macOS has a whitelist. So if you buy a PCIe to Thunderbolt bridge and the Thunderbolt bridge is on that whitelist, any PCIe device you put behind it will have DMA access. So for other issues with this Thunderbolt access control, you can see our paper. Mm-hmm.
That would be more for a peripheral vendor to have the appropriate certification for their product.
Yes.
And verification on the OS side.
Mm-hmm. Yes.
Czy jeszcze jakieś pytania do prelegenta? So thank you, Brett, for this impressive research and the presentation.
Thank you very much for having me.
My question would be, how big is the community? You mentioned that it's open source and there's a mailing list for anyone interested in the continuation or, you know.
Yes, so we made this work public in February, only a few months ago. So the community is Actually, for the amount of time that it's been out, it's reasonably large. We have, I think, between 10 and 20 people on our mailing list, and we know that at least 4 or 5 other different sites, different companies, research groups, etc., they're setting up their own versions of Thunderclap. So I think, given how short a period of time the work has been public, and the work has actually been accessible for people to access and grab and try for themselves, it has some momentum now.
Okay. Thank you.